Hello, my name is Alistair Adcroft, and today we're going to walk you through running the double gyre experiment for longer and then visualizing some of the output. So in the last tutorial we ran double gyre, but we ran it only for 10 days, which is the default length of the run. So the first thing is to look at what parameters control the length of the run, and before we get into even that, I want to show you how the parameters are read into the model. So the first one I'm going to look at is input.nml. And this has, in ocean-only experiments, just this one nameless block that we care about, MOM6 NML, and there's one parameter in particular, which is parameter file name, which is a list of strings, and those are file names from which the model will then read parameters. Those file names can be anything you want. We have a convention of using MOM6 and MOM override, but you can change those files to anything you like as you see fit. Let me show you first of all what the parameter files look like. I'm going to do so by showing you output from the model rather than input. MOM6.all is a documentation of all the parameters that the model is aware of in this particular configuration. And it returns, it looks like this syntax is parameter equals value. And we have a lot of comments over here which are produced by the model. This is the documentation of these parameters. We often have units, default values, and explanation of what the parameters are. The parameter we're interested in today is daymax, and you'll see that it is set here to 10 and that it has units of days. In this particular instance, those units are actually determined by another parameter slightly higher up in the file. The parameter time unit specifies the unit for specifying other time-related parameters such as daymax. So here it's set to 1 day in seconds. So daymax is 10 here. There's no point editing this file because it's generated by the model. So I'm going to actually go to MOM6 and show you that that's where daymax was set the first time. So here it is, daymax equals 10, and you'll see this is just a simple cut and paste from MOM6.all into MOM6. That's how we created this file. Now we could change daymax here, but I'm actually going to show you how MOM override works. MOM override is normally shipped as a blank empty file, and what we're going to do first is just add the line daymax equals 10.0. And if I run the model like that, the model will happily ingest those parameters and carry on as if nothing was wrong. Because nothing really is wrong. We specified daymax twice, but we specified it with the same value here. To prove that it is actually reading that second line, I'm now going to change daymax to 200, because I would like to run the model for 200 days, and I'll run the model again. And now the model comes down with a fatal error. Here it is, fatal MOM file parser. Daymax was found with multiple inconsistent definitions, 10.0 and 200.0, and so the model came down because there was an ambiguity in the way we specified the parameters. So the way we're going to overcome that is we're going to go back to this second file, MOM override. I'm going to insert in front of daymax equals 200 the keyword #override space, and that will tell the model to give precedence to this line. Now I'll just prove that that will work by running the model now, and there it is, happily loaded up and carried on. But before we actually run the model in earnest, I also want to change the frequency of output for the model, and we're going to do that by going to the diag table. And here I'm going to simply go to the first registration for a file, this prog file, %4 year, %3 day, which is going to be a new file for every year, which is going to have in it the variables u, v, h, and e, which is specified lower down. I'm going to change the frequency from 5 days to 1 day. Okay. So I'm going to write that file, and now I'm ready to run the model. So I'm going to launch that. And when it's finished 200 days, I'll come back. Okay, the model's finished 200 days, so now let's look at the output. So first let's look inside the directory, and you'll see that after the file that we last edited, which was MOM override, and the model and diag table, the model has generated a whole load of netcdf files with the output, and of course the updated documentation of the parameters. And so this is what we're going to be looking at next. Now I'm going to do the analysis with a Jupyter notebook, and if you haven't got access to that, you can easily install it from the web by doing a Google search on install Anaconda, which we use for managing our Python installations. The first link is, or should be, Anaconda install, and you'll have instructions there for your platform which, oops, I went to the wrong one there, but anyway, I've done this already, so I'm not going to walk you through the steps, but you can follow that. It's fairly easy, it doesn't take very long. Okay, now, in the new window, I'm going to start a Jupyter notebook, like so, and this will open up a new window for me, which I'll make full screen. And then this is, you'll see that this is a directory view of the directory we just started this notebook in. And so there's all our output in these files. And what we're going to do is create a new Python 3 notebook in this location. And we're going to use Pylab for getting all of the various modules that we need for convenient visualization with matplotlib and so on. And I'm going to instruct Pylab to do the figures inline. And I'm also going to use SciPy's IO netcdf library for actually reading the data. So execute that. Right, so now, first thing I'm going to do is create a handle, I'm going to call it prog file, to the prog file, and there it is, and I'm using tabs to get lists of options for me. If you're not familiar with IPython notebooks, you'll love that feature. So let's execute that, so that loads fine. So let's examine that object prog file. If I do a dot, it gives me a whole list of attributes which I can look at, and the one I'm going to look at here is variables. Execute that, and you'll see those are the variables which are in this file, prog 0001, 002. Now each of these is a SciPy netcdf variable object, and I'm going to create another variable to point to one of those. So I'm going to call it eHandle. It's good to think of them as handles. And to get it, I'm going to go to prog file dot variables for the variable e, and now eHandle is an object in its own right with a whole load of attributes. So for example, eHandle has a long name, and if I just execute that, it will return the value of that, and this e is the interface height relative to the mean sea level. Another thing we're going to be interested in is the shape of this data. So eHandle.shape, excuse me, oops. And so this is the shape. So we have 200 records. It's a 4D array on disk, but it's got 200 records of 3 dimensions, 3 interfaces, 40 points in the j direction, and 44 in the I direction. Okay, so now let's see what can we do with this. The first thing we can do is do a plan view snapshot of E. So pcolor mesh is a good tool. pcolor mesh is a lot more efficient than pcolor. It can handle curvilinear grids more easily. So I'm going to look at eHandle 0,0. So the first index is referring to the time index 200. So it's the first record in Python starts at 0. First time record, and the top interface is 0. So let's execute that. And there we have a snapshot now. I haven't got any color bars, I don't know what the values I'm looking at are. So the first thing I'm going to do is add plot.pcolorbar to that line. And if I execute that, there's the color bar. Now I just want to point out one little detail. When you don't put a semicolon at the end of a matplotlib command, you get a matplotlib handle of some form of memory address, which you can hide by putting a semicolon after the last command. And there we are, it's disappeared. Good. Okay, so that's a snapshot. We could look at different times. We could rerun this command, say, look at it in the 100th record. That lets you peruse data somewhat inefficiently. And so one thing I'd like to do is show you how to do some animations rather quickly and easily in an IPython notebook. So the first trick I'm going to show you is to actually use a widget, which is an interactive image. And to do that, we're going to import IPyWidgets like so. And IPyWidgets will provide several tools, but the one we're going to use is the interact tool. And to use that, we have to define a function that does the plotting for us. So I'm going to define a function, plot SSH, and it's going to take a single argument for now, which can be the record number that we want to display. And then we're just going to put in the same commands we used before for making an image. And we're going to plot the particular record, which is the argument of the function. And then we put in a color bar. And then let's just test that with plot SSH. Let's look at record 0 first. Okay, there we are. That's a similar plot to the one we've seen before. Now, if I was to change the record argument to, say, 100, like we have done earlier, you'll see that it reproduces the figure above, but of course the color bar is changing. And when we're animating or perusing this data, we'll want to have a fixed color scale. So what I'm going to do is just check to see what color range, what range of values we should be looking at. So let's look at eHandle, all time slices of the surface, and look at the min, and likewise for the max. Let's see what the values. So the C-surface height is varying from -1.5 to 0.8. So in our function, I'm going to put in a plot clim, which is going to fix the color range from -0.5 to 0.8. Okay, so there is 100th record on that scale, and now we can skip to 200th record. Oops, I was out of range, sorry. Let's go for 140, and there it is. Okay, so now that's working, I'm going to now invoke that function using IPyWidgets interact function like this. First argument to this function is the actual function we've just written, plot SSH, and then we're going to specify that record should be varying from 0 to the number of records, which is handle.shape, first axis -1, and then we're going to have intervals of 1. Now when I execute that, now what happens is that the figure is drawn and there's a new slider that's appeared up here, which is currently set at 99. And if I slide that slide back to the beginning, you'll see that the image updates to the beginning value, and then I can click this slider along and see the image evolve. So that's one way of perusing three-dimensional data, using a slider to specify one of the axes. And then the other way I'm going to do things is actually do an actual animation in the page. And to do that, I'm going to use a different package, which is provided by the Jupyter Notebooks itself, IPython. And from IPython, I'm going to import the display module. And this time, I'm just going to write a loop that goes from n to the number of records. And oops, put too many brackets there. And then this is now going to have some little bit two special commands here: display, and I'm going to pass to display the handle for the current figure, which is obtained by plot GCF. Then we're going to declare the figure, and then we're going to plot the figure. I'm going to use the same function we used before, SSH, and pass it n. So we plot each record consecutively. And then after you've done the plot, you then need to use display.clear output, which is going to only act when the display needs to be updated. So that wait equals true will change that behavior. So now when I execute this loop, there is lots of frames of SSH being animated forward in time. Okay, so two quick tricks for animating or looking at three-dimensional data. And this is hopefully going to get you started looking at some of the MOM6 output.